Hey there. Today we're going to talk about taking integrals in higher dimensions. So we're first building up the theory of integration from the idea of Riemann sums, just like we did in functions of single variables. So let's first go back to that functions of single variables, remember how that worked, and then bring that over to higher dimensions. All right, so what we're thinking here is we're thinking if we have a function and we'd like to figure out what the area under the function is between A and B, so find this area. And remember, this is a signed area, so if the area is underneath the axis, then it counts negative. If it's above the axis, it counts positive. So we're trying to figure out what's the area inside this region. So the way we realize that to calculate an area, areas of really strange regions are hard to calculate, but areas of rectangles are super easy to calculate. So we take this region, we break it down into a whole bunch of smaller regions, right? We say we're going to call this A, we're going to call x naught, the next one we're going to call x1. Let me zoom in a little bit here. The next one we'll call x2, the next one we'll call x3, dot, 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 up to xn. And then each of these, the distances, we'll call them delta xi. So x1, delta x1 is what happens between x0 and x1. And we choose some point in this region. So let me zoom in here. And so we've chopped down our region into a whole bunch of smaller pieces. They don't all have to be the same size. We choose some point in this first region and we call that xi star. So this is x1 star. The next one would be x2 star. And we look at what the function value is at x1 star. So we've got our region here. The function value at x1 star is some value, and we use this to approximate, we use this as the height of the rectangle so that the area of this one rectangle is delta x1, that's this width, and the height is f of x1 star. And so we do that for each of our regions. For x2, we also do this. We get f of x2 star, and the width here is delta x2. And what we get is we get a bunch of rectangles, and we like rectangles because we know what the area of those rectangles are. So we've taken our sum here, we add up all those rectangles, and if we then make these rectangles smaller and smaller and smaller by making the width smaller and smaller, chopping it up into more and more intervals, then the integral that we get is the area is the limit of these Riemann sums. So what we're doing here is we're adding up a whole bunch of rectangles, the area of a bunch of rectangles, and from that we get the area under the curve. So if we take this limit as this width goes smaller and smaller, we get that the limit of this gets closer and closer to the area. If that limit exists, that's what we call the integral. Okay, so that was Calc 1. Now we're here with multivariable calculus, and instead of having a picture in which we have a function and we're looking at rectangles underneath it, now we have a surface. And instead of looking at this surface over an interval, what we're doing is we're looking at the surface over a rectangle, and we're asking what's the volume of this surface, what's the volume underneath that surface. Alright, so how can we approximate that? So the way we go about approximating that is just like we did before. We divide this into rectangles. Now, this is the x-axis, so we divide the x-axis into a bunch of slices. We divide the y-axis, the y-interval here, so if this is going from A to B, and y is going from C to D, we chop each of those pieces into some number of intervals. So we'll chop this into m different slices, we'll chop these into n different slices, and just like before, it's when the surface is curved, it's hard to know what the volume is underneath the surface because it's not pretty. But if we approximate the volume by a whole bunch of rectangular prisms, we know what the volume of a rectangular prism is. The volume of a rectangular prism is the area of the base times the height. So in the same way that the area of one of these slices over here was the width of the thing, delta xi, by the height, which was f of some point in the in that interval, the ith interval. The same thing is going to be true. We choose some special point in here. That was not a good color. We choose some special point in here, which we'll call xi star comma yi star or yj star. So, and then this interval right here corresponds to delta xi, and this interval right here corresponds to delta yj. So we could, for every single choice of I, and for every single choice of j, so I is in the x direction, j is in the y direction, for every choice we get a rectangle in the base, and then the height is going to be corresponding to the function value at xi, yi. And so the height, so the volume of this one piece that corresponds to I in the x direction and j in the y direction is, this is the height, this is the width, so I don't want to divide by h, I'm just saying this is the height, the width is delta xi, and the length is delta yj, and so that's the volume of one piece. And if we add up over all the pieces, we get this double sum where we're summing up over all possible i's and all possible j's of this delta xi, delta yj, which we can think of as a delta area. And that's going to approximate the volume of the surface. And just like before, if we're going to talk about if we take the limit as those areas get smaller and smaller, as the delta x's get smaller and the delta y's get smaller of this Riemann sum, that's going to be our definition of what the volume is under the curve. That's going to be our definition of this double integral. So we're using two integral signs here because this is a function of two variables. Later on, we're going to be talking about functions of more variables, so a function of three variables will have a triple integral sign. This little r here is telling us the region that we are chopping up over, and this is our function, and we use dA to represent a little bit of area. So I like to read this expression as, what is the volume under the surface f of xy above the region R? Or, in other words, what is the volume if we chop up into little bits of area chop up the region into little bits of area, and we add up the volumes of each of those little bits. All right, so let's maybe put this a little bit into practice. So the first thing, to allay many of your concerns, this function, this was defined in terms of a limit. we're going to be working in this class normally on continuous functions. If you have a continuous function, the limit will always exist. We're adding up the volumes of a bunch of rectangular prisms. And so let's do an example where we do a Riemann sum to approximate the area. So consider this surface 16 minus x squared minus 2y squared. All right, I'm going to draw this picture. We have R. So we're going to always have two pictures here. When we're dealing with the volumes, it's really important to think both in terms of the xy plane and then also in terms of the xyz space. All right, so what we're going to do is we've got the x and y, and we're saying we're going from 0 to 2, and then from 0 to 2, and this is our region that we care about. This is the region that we are integrating over. We see this surface 16 minus x squared minus 2y squared, and if you think about what's happening with this, if we had z is equal to x squared plus y squared, that's a paraboloid going upward. And so similarly, z plus x squared plus 2y squared, that's a elongated paraboloid. And so 16 minus that is taking that, flipping it upside down, and then shifting it up. So if I'm drawing a picture of what this looks like, we've got this paraboloid that has been raised where z is equal to 16 at 0, 0, and it's a paraboloid over the region. So if I'm drawing a picture in 3 dimensions, this was just an idea about what this shape is going to look like. In 3 dimensions, over our region, so this is from 0 to 2, this is from 0 to 2. Over this region, we have a paraboloid. When x is equal to 2, we get 16 minus 4, so that comes down like this. And when y is equal to 2, 2 squared is 4, minus 2, so this one goes down like this and like that. So we get this shape. This is what our surface looks like, and we're looking for what the volume is underneath the curve here. All right, so this region, so what we're going to do is we're going to approximate it using 4 different squares. So we take our region, right, this is x, this is y, this is x, this is y, and we break this up into 4 different squares. And we say, all right, so then these are the delta x's, and these are the delta y's. And so what is the area of one of these squares? Well, the area of one of these squares, if we look at this went from 0 to 1, so delta x is 1. And this went from 0 to 1 as well, so delta y is 1. So delta a, which is equal to delta x, delta y, is equal to 1. All right, so when we're doing our Riemann sum, we're looking at each of these squares, and the area, the delta A, is equal to 1 in each of them. So what we're going to get is, we know that what the area is, and now we need to choose what our point is above the curve. So we can either choose to do, if we look at the shape of this curve, if we choose, for instance, this as our special point in the in the square, then we can see that that's going to be an overestimate for what the function value is. If, on the other hand, we chose the other corner, the upper corner, the 1, 1 corner, then that would correspond to being here, and we would get a height that's lower than the function value over that whole interval, in the whole mini square. So depending on the point that you choose, you're going to get a different approximation for what the function is. So let's choose these red points. Maybe we should just do both of them and look at what's happening. So let's choose for each square, for each sub-region, choose the lower left corner. So maybe we'll call that the southwest corner. And what that corner is the smallest x value and the smallest y value. And so for this first square, that's the point 0, 0. So this is going to be the height times the area, delta A, plus the height for the next square, we need the corner that is at 1, 0 times delta A, plus f, so now the next square up here gives us f of 0, 1 delta A, and the last one is this one, f of 1, 1 delta A. This is going to be that the volume is going to be approximately the height times the base, the height times the base, the height times the base, and the height times the base. These are the sum of the volumes of each of the smaller pieces, right? So this is going to be for this one, and then when we're at this point, the height gives us this. And then for this one, where are we? We're here. That's going to give us this rectangle, this rectangular prism, and this one's going to be here. That's going to give us this rectangular prism. So what we've done is we've taken the volume under this curved surface and represented it by 4 different rectangular prisms. So here we plug it into the function. So 16 minus 0 times delta A plus f of 1, 0. So that's 16 minus 1 minus 0 delta A plus 16 minus 0 minus 2 delta A plus 16 minus 1 minus 2 delta A. And so that's going to give it, and since delta A is equal to 1, the final answer is going to be 16 plus 15 plus 14 plus 13, which 30, 45, 58 cubic units. And that's going to be, we said that's going to be an overestimate for what the volume is going to be. If instead we used the other corner of this region, instead of being F00, that would be F11. That would be the upper right corner. So that would be F11. This would be, so in this region, the upper corner here is F21. This one would be F12. And this one would be F22. And so if we were to go through and set up this integral, what we would get is it's not an integral yet, it's the Riemann sum. If we were to do this, we would get a lower estimate for what it would be. It looks like it's going to be 13 plus, if we plug in 2, so 3, subtract 3, so 10. If we then do, so this is 16 minus 2 minus 2, 16 minus 4 minus 2, then we get 16 minus 1 minus 8, and then we get 16 minus 4 minus 8. So 16 minus 8 is 8, 7, and the last one 4, so a lower estimate would be 2034. All right, and let me just now say one thing that's going to be true for all of your integrals, these double integrals. I'll go here and I'll just use this blank space right here. So if your region has area A and the maximum value of f of xy on R, so this region R, is capital M, and the min value of f of xy on R is little m, then what we know is that the volume under the curve of f of xy dA is going to be between little m times the area and big M times the area. What we're saying is that if your region looks like this, and you have a surface over it that has some max value, capital M, and some min value, little m, then just by doing a really big cylinder over the A, this is a lower bound, which is m times the area A, and this is an upper bound, which is capital M times the area A. So this is one property. It shows up in section 12.2, but I think it really fits better here because it feels a lot like a Riemann sum with just one region instead of chopping it up into pieces. All right, we're going to stop here for today. Next, we'll do some double integrals with no Riemann sums. See you shortly.